Hello, my name is Jeremy Lopez, and my project focuses on the semi-supervised learning model. And so, a quick overview of it is so basically the kind of business problem that of my project is kind of predicting the duration of testing a Mercedes-Benz car based on its features. What combination of features it has. And the actual features themselves are anonymous. So in the data set, you'll see them labeled as X0, X1, X2. So you won't know exactly which feature you'll have available to you. In the combination of features, as you'll see later on. And so to tackle this problem, we're actually going to be using a semi-supervised learning method known as pseudo labeling because the data set I chose to use had a fair amount of unlabeled data. So what pseudo labeling does, it'll actually predict the labels that and actually give them what's called pseudo labels for the unlabeled data. So before we do all of that, though, there's some things we have to do. Which first we will have to pre-process some data. As you see later on, there are some non-numerical values in our data, so we have to transform those into numerical values. And then later on, we'll see that we'll actually be kind of comparing models because there isn't a kind of default pseudo labeling model in the scikit-learn library. So we actually have to implement our own, and in order to implement our own, we're actually going to be using another model kind of underneath it. But you'll kind of see what I mean later on when we actually implement the model itself. And then we'll actually compare it to the default model that we chose to use. Again, this all makes sense later on. But before we kind of move on, we have to kind of know what exactly semi-supervised learning is. So what I did is create this background section. And of course, in order to know what semi-supervised learning is, you need to have a good understanding of what both supervised and unsupervised learning is. So real quick, I have here kind of highlighted some comparisons between the two and kind of summarize what both of them are. So with supervised learning, you have both an input variables and an output variable. So mathematically, you can think of it as y equals f of x. You have your function, you plug in your x, you get out your y. Simple as that, mathematically. So another kind of good way to look at the actual process of an algorithm learning from the training data set with supervised learning is how it gets its name is a teacher-student situation. We can think of the student taking a mastery quiz, and if you don't know what a mastery quiz is, it's just a regular quiz, but you don't pass it unless you get 100%. So you're gonna keep taking it over and over until you get 100%. So that's sort of how it works. A teacher supervising the learning process, which is you taking the mastery quiz. And obviously, since the teacher made the quiz, the teacher has the correct answers. So each time you're done with your quiz, it'll be corrected by the teacher. And so you could say say for your first try, so you haven't studied at all, you don't know much about what's going to be on the quiz, and you kind of just guess. Once your quiz is corrected, and you probably won't get 100% on your first try. You have to keep trying, but each time you learn something new. You say, oh, okay, the first question isn't this, or it is this, so you learn something new, okay. But the problem is that the next quiz might have some different questions, but eventually you do learn something new each iteration, each quiz, and eventually you'll get 100%. And that's just for one quiz though. So then you have to move on to the next quiz and kind of pass them all. And once you pass all your quizzes, that's sort of where the learning stops. Kind of this right here. When you achieve an acceptable level of performance, when you have all the knowledge you need for the quizzes. So that's a cool way of looking at it. If you have some trouble figuring out what exactly supervised learning is, that's kind of a cool way to look at it. But some examples of supervised learning that, if you're taking this class, you kind of already you've seen this a lot, I'm sure, even if you haven't taken this class, probably. So classification, you have your input data, and then your output would be a category. So here, kind of like red, blue, disease, or no disease. Anything that's a category would be your output variable, and with regression, your set of category, you'd have a real value. So like anything that's a numerical value, usually like dollars or weight, you can attach some sort of numerical meaning to it. And some other kind of popular examples would be like linear regression or random forest, which can be used for both classification and regression, or SVM for classification problems. So just by the way I'm describing all this, you can kind of tell that supervised learning is usually kind of more popular than unsupervised learning, and there's a good reason for this, because with unsupervised learning, you're dealing with the you have your input data, but you don't have the corresponding output variable. So really, all you can learn is just learn more about the data you have. Kind of model out the distribution. So the student teacher kind of scenario is a little bit weird here because there is no supervising teacher, right? And without the teacher, you won't know what the right answers are. So you're kind of just left on your own to kind of learn, through the quizzes. If that makes sense at all. This scenario doesn't work exactly with unsupervised learning, but um, again, if you're taking this class or if you're taking it right now, you've probably seen clustering for sure, an association. Um, so with clustering, what you want to learn about the data is the actual groupings. So like grouping customers by what they purchase is an example, and with association, you want to discover some rules that kind of describe what your data is doing. So like people who buy X also tend to buy Y, that sort of stuff. So the kind of main difference between supervised and unsupervised learning is basically just the input and output data, and also whether they have labels or not. So unsupervised learning, you would definitely need to have labeled data. Unsupervised learning, mostly use unlabeled data, and then you have semi-supervised learning. So that's sort of a middle ground, kind of in between supervised and unsupervised learning, which is in the name, semi. So here you would deal with a large amount of kind of available input data. You have your input data. You're always gonna have that, but only some of your output data is known. Your Y's. You don't. Not all your data is labeled. So that's what semi-supervised learning deals with. Specifically, what pseudo labeling is sort of kind of predicting these labels. For your unlabeled data. And then you can, after you kind of make predictions for the unlabeled data, you can make a traditional supervising learning model, which we're actually going to be doing later on, in hopes that pseudo labeling will actually make some improvements by predicting your own unlabeled data. So pseudo labeling is the technique we're kind of going to be using for this project, for our model. So this image right here is sort of a good summary, a good explanation of what it is. It's really not that hard to understand at all. If you understand supervised and unsupervised learning, then this should be pretty easy to understand. So you just train the model on whatever available label data you already have to start out with, and then you would use your trained model, and then you would make these predictions for the unlabeled data, and which creates these quote unquote pseudo labels, and then you would combine your newly labeled data with your already labeled data, and then you use that data set to train the data. So now that we kind of have a good understanding of what kind of we need to know, we can look at the data. So the data set we're using is actually from the Mercedes-Benz Greener Manufacturing Catwalk competition. So if if you're interested in looking at that data set, it's right there, the link. And this code block, all we do here is really just load our data, our train and test sets, and here you can have a good look of what the data looks like originally. So like I said before, we have to do some pre-processing because there are some non-numerical values, because these first couple of features are categorical variables. So we'll actually have to turn these into numerical values, which we do in this code block. And really this label encoder is really what does most of the work. The code itself isn't too complicated, so all we do is we turn these columns into lists for both the test and training sets, and we just feed them into this label encoder and then transform them into numerical values. So that does all the work for us there. So you can see that's how our new kind of transformed data set looks like. We have all numerical values now, and we can go on to the actual model implementation itself. So first, like I said, we have to make our own implementation of the pseudo kind of labeling model, and this function itself, it makes a training data set that has both our originally labeled data and our newly pseudo labeled data. So it does two things at once. First, it actually creates these pseudo labels that we're going to need in our training set. So that's done all here. And then so the creation of the pseudo labels happens here, and then we actually add it to the test set here, and then yeah, I mean basically that's kind of, again, I don't want to get too deep into this code. that's basically what it does. It'll just add in. It'll make a training set that has both pseudo-labeled and labeled data. But one thing I do want to mention that's kind of important is this sample rate argument right here. What that does, it sort of controls how much of the newly pseudo-labeled data you add into this new training kind of data set. If you set it to 0, then it'll just use all the originally labeled data and none of the newly pseudo-labeled data. But if you set it to like 0.5, then you will still use all of your labeled data that you had in the first place, but you would also add on half of your newly pseudo-labeled data that you created through this function. So next, we also need to kind of make our own fit method function because again, the default models don't account for the pseudo label data that we've just made. So I mean, really, it's just the same function. All we're doing is accounting for our new augmented training set. But again, if you set it to 0, then you're not adding in any new pseudo labeled data at all. So it would just be the regular fit function. The models default to originally. So before we go on, you can kind of see that the arguments for both of these functions are a lot. And there might be kind of situations where we might want to add in more functions. So the easiest way to do that is just create a class. So you can see some of the arguments from the past two functions can be initialized within this class right here. So you just kind of define it once and then don't have to worry about it as much. So again, here are our previous two functions are right here. You can see there's a lot less arguments in here now. And then again, we can add in some new functions like the predict, which really it just uses a default predict anyway. But it kind of shows you that this is a lot more cleaner and kind of more efficient because you could just add in functions here instead of just using them on their own. So I mean that's really all there is to the actual implementation of it. So if you notice, in the arguments themselves, there's a parameter called model, and what goes in this model is a model. But you could put any kind of default out of the box model that's already in the scikit-learn library itself. So you can see some examples here. The XGB regressor model, the Bayes model, K-neighbors, random forest, all of these are models that we can use in our implementation to make our own pseudo-labeler model. So like I said in the overview, we're actually going to be using a kind of out of the box model beneath our newly implemented pseudo-labeler model. So to find out which one we should use, we're actually going to be comparing the coefficient of determination as a metric value, the R2 score sort of. That's done here. This code just kind of just does all that for us. So it'll get the R2, the mean score of each model and also standard deviation. But if we kind of compare the mean scores of each of them, the XGB regressor does have the highest score, along with an average standard deviation. But then again, the standard deviations are really too different from all of them. So therefore, we're gonna be using the XGB regressor model to make our own pseudo-labeler model, and you can actually see how that's done in here. So here, pre-processing data, we just kind of make our tests and training sets. Here is where we actually make our model. So here's our own custom pseudo-labeler class that we made previously. And here is our XGB regressor model, which is the model we're going to be using to implement our own model. And you can see at the results, I should probably explain what all these numbers mean too. That's probably pretty important. So basically, like I said, all these X values are features. So it's 385. That's a lot of features. Also, another thing I want to kind of mention is, usually if you're not doing pseudo labeling, you probably want to kind of do some feature reduction or dimension reduction, because that's a lot of features. So, but in our case, we're more worried about the actual labels rather than the actual features themselves. But what really matters is the kind of ratio of unlabeled data and labeled data. And this data set kind of used because it's a pretty good data set for pseudo labeling, because about half of the data is labeled and the other half is unlabeled. And so, say like the 10% of data is unlabeled and 90% of your data is labeled, then doing this kind of a pseudo labeler thing probably won't be as efficient. It'll probably just detriment our the default model's performance. But as you'll see later on, we actually do get a slight improvement. But anyway, what this does is basically we have a combination of features right here. So these are usually binary, whether it has a feature or not. So our ID 0, our kind of 0th vehicle, has this 377 feature. It does not have the 376 feature, and so on. So this is a combination of features right here, and this Y would be the amount of time it took to actually test the vehicle itself. So you can see it with our first kind of vehicle 0. We go down here to kind of this array we get here. Our model would predict that it would take about 117 seconds to actually test the duration, or test the vehicle itself. So that's what all these numbers mean. Probably should explain at the beginning, but now we can kind of move on to the performance of our newly implemented model versus the the model that's underneath it, the XGBoost regression model. So again, the same method that was done to evaluate these models back here will be done here. So it's the same process. Again, we are doing we're comparing the R2 mean values again. But so you can see that there is a very slight improvement, like very slight. But again, this data set was from a Kaggle competition, so this sort of improvement does actually matter, in terms of like leaderboards and all that kind of stuff. But from the business perspective, for our business problem, this really isn't much of an improvement. Kind of pseudo labeling. It's cool that it lets us kind of use unlabeled data, while training these machine learning models. It's pretty powerful, I think, pretty powerful tool. But at the same time, it doesn't really offer too much of improvement, in terms of kind of our business solution that we're aiming for. All the time we spend making, all this, we probably could have made some improvements to the actual default, XGBoost regression model itself, rather than making a pseudo labeler. Yeah, I mean, while there was a very slight improvement, it is an improvement, So I guess what I'm trying to say is, there is potential, I guess, in maybe a different data set or another situation, this kind of pseudo labeling technique will maybe have a drastic improvement on a model. But from what I've seen through kind of my research and through all these references, usually kind of pseudo labeling doesn't have a drastic improvement on models. So from a business standpoint, this probably wouldn't be really effective at all. That kind of slight improvement probably doesn't make a difference at all. And all the time you spent again making this model, you probably could have went back to maybe doing some dimensionality reduction, getting rid of some of these features, kind of from there going on to kind of find out, maybe test a couple of different models and go that route. But again, in the end, we did get a pretty decent score, I think. I think was pretty high on the leaderboards on the Kaggle competition website. So with that data, we can kind of predict which combination of features would take the longest for testing, and which takes the least from what we've predicted there. So that is basically my project.